In this video, we're looking at the wave-particle duality, and we're really looking at the intro to light and photons. So the science theory for this lesson is that interacting matter, light, behaves like particles, which we call photons, with a certain energy given by E equals hf, and a momentum P equals h over f, where h is Planck's constant, f is the frequency of light, and lambda is wavelength. The key learning intention for this lesson is to calculate the energy and momentum of photons in various regions of the electromagnetic spectrum. This lesson is the first point that we question what light is. So far we've seen in the double slit experiment, in the diffraction grating, it follows the behavior of a wave. We see that interference pattern, and that makes sense. However, when light interferes or interacts with matter, the wave theory of light doesn't explain the results. Instead, we find that the effects of this can actually be explained if light is a physical particle rather than just a wave. As a result, we now say that light is both. It's a wave and it's a particle. It is not one or the other, it is both. And this is where we have that term, the wave-particle duality, because we describe light as a wave and a particle. The first example to prove this is that when light interacts with matter, it does so in a manner that cannot be described in the wave motion. Interference and diffraction, as we saw earlier, are properties of waves, which indicate light is a wave motion. However, there are other phenomena that require alternative explanations. If we use a very low intensity light source, an image can be seen slowly forming as more and more of these individual pieces of light form on the screen. It's a bit like having a really long exposure time of a photo. You can see that it slowly develops from small dots all the way up to the higher resolution picture. The same effect can actually be seen using a two-slit interference pattern over time. You can see the pattern very slowly forming. It's like adding more and more paint to the canvas as time progresses, until we get our very solid, clear lines. So this is on more like a photo screen where it's developing versus just staring at a wall. These pixels or spots that we're seeing form the image are actually photons. Photons are considered discrete packets of energy, so they are actually energy particles. Each photon has an energy given by the equation E equals hf, where h is Planck's constant, given on the formula sheet, 6.63 times 10 to the negative 34 joule seconds, and f is the frequency of light. Each photon has a momentum given by P equals h on f, and the equation V equals f lambda, the wave equation that we've seen before, applies, or we could use C equals f lambda, because the speed is the speed of light. So C being speed of light equals f lambda. We can use this to find the wavelength when the frequency of light is known, and vice versa. Everything we see in our lives is actually made up of loads and loads of these photons. Images, our vision, all of these are things are seeing billions and billions of individual pixels, which are actually these photons hitting our eyes. It just moves so fast that instead of forming that slow image that we saw earlier, it seems to be almost instantaneous, or for us, it is instantaneous. The energy of the photon is given by this equation, as we saw earlier, E equals hf. Notice that the constant is very, very small, so therefore the energy that each photon has is also very, very small. This links with learning intention 1, calculate the energy and momentum of the photon. Here we are calculating the energy using E equals hf. The energy is directly proportional to its frequency and inversely proportional to its wavelength. If we look at the equation frequency equals speed of light, remember this used to be v, but now we're talking about photons, so speed of light divided by wavelength, we can see that if we have c as the speed of light, we substitute that back into the E equals hf equation, we get this new equation where we say the energy is equal to Planck's constant times the speed of light divided by lambda, which is the wavelength. So now we can see energy is inversely proportional to wavelength, and in this original example, we saw it's directly proportional to frequency. So high frequency light, or waves, or anything in the spectrum has a lot of energy, as we saw before in the EM spectrum intro. Now we can see that with photons as well. Let's look at the momentum of photons. When light interacts with matter, it behaves like a particle, which is now we know as a photon. One of the fundamental principles of the interaction of particles is the conservation of momentum, and we've seen this in the earlier chapter. American scientist named Arthur Compton experimentally found that when a photon hits an electron, they acted in such a way that the total momentum before and after was the same, so the momentum was conserved. It obeyed the law of conservation of momentum, which also then reinforces the fact that it has to be a particle. The conservation of momentum was developed for particles, with both mass and velocity being important. But how does this work with a photon? A photon has no mass. How can it have a momentum? Does light even have a mass?
Get on with it. Yes, get on with it!
Oh, I am enjoying this scene.
Get on with it!
In answer to that, it comes from Einstein's theory of relativity, E equals mc squared. Einstein implied that mass and energy are interchangeable. So we don't necessarily have to have mass in order to have energy. The energy can act in the same way that the mass does. Matter can actually be destroyed or created, and energy is replaced or gained or lost in its place in order to not break the law of conservation. Although photons are constantly moving, they have no rest mass. The energy of a photon can be equated and relativistic mass can be found. So if we use this equation E equals hf, but we also said that E equals mc squared, if we equate the two and find m, we get this equation where the mass of a photon is Planck's constant divided by the wavelength of the particle, or the photon, multiplied by the speed of light. Now we can determine the momentum of a photon. If the momentum traditionally is P equals mv, we can then substitute that mass for h on lambda c times c. C's will cancel out. We get the final momentum, Planck's constant divided by wavelength, equals momentum. So the fact that a photon has energy and technically no mass is enough to still give it momentum. This is how the solar sails worked from the previous chapter that we saw, where the light would bounce off the sail and give it a push. Despite the fact that there's no mass to actually push with, we can have this relativistic mass based on the energy of the particle. The result of this is that high energy has high pushing power in terms of light sources, and low energy has very little pushing power because it has a low momentum, or a small magnitude of momentum. Let's have a go at some practice questions. So here we're looking at calculating the energy of photons, calculating the wavelength, the momentum, and determining the frequency. So this links with the learning intention, calculating energy and momentum of photons in various regions of the electromagnetic spectrum.
Speed of light. Speed of light.
Tell a minute.
Speed of light.
Speed of light, I'm breaking down like this ain't nothing new. She wanna kick it, don't skip it, let's say we rendezvous. Usually I don't trick up, pick up like one or two. Them daisies known to be deadly, especially if I love you. I've grown impatient, I'm tired of waiting just for you. If we gon' trip, then we taking trips out to Malibu. My alley-oops, we returning troops from a blowing nuke. A bomb crash and I'm slow asking to tell the truth.
Taking off, yeah, I'll be on my way now. Feel it in the air, cause I'm in a better place now. I never doubt it, no I never doubt it. If you don't like that, leave it where you found it.
Yep. I ain't cutting that pie, I'm saving half for you. Yep. I ain't cutting that pie, I'm saving half for you.
Hey Taylor, I got you. Look, I'm saving half for you cause I got it bad for you. Don't you ever trip about it, we can even passport it. You deserve it, you ain't even gotta ask for it. Life's a marathon and I wouldn't wanna fast forward. And for the love, it was back and forth like tennis. Indy down to Atlanta like every weekend, no matter what we had on the schedule. Progressing with every pedal, momentum at speed of light. I need me like 20 medals, yes. Taking off, yeah, I'll be on my way now. Feel it in the air, cause I'm in a better place now. I never doubt it, no I never doubt it. If you don't like that, leave it where you found it.
Break it down, nothing new. Let's say we rendezvous. 1 and 2, special
Alright, let's have a look at some answers. So firstly, we just plug in our E equals HF. We get 2.84 times 10 to the negative 19 joules. The wavelength, we use V equals F lambda. And we rearrange for lambda, we get 6.99 times 10 to the negative 7 meters. To calculate the momentum of the photons in red light, we use P equals H over lambda. We get 9.48 times 10 to the negative 28 sec newtons. So remember, sec newtons is the momentum, or you could use kilogram meters squared per second squared, which would also work. Determine the frequency of the X-ray photon. In this case, we were given EV, so we needed to convert that to joules, so we multiply by 1.6 times 10 to the negative 19. We get our 1.53 times 10 to the negative 14 joules. And then we plug that into the E equals HF equation, rearrange for F, we get 2.31 times 10 to the 19 hertz. From here, have a go at the workbook questions for this lesson, and I'll see you next time.
Well, that's the end of the film. Now here's the meaning of life. Thank you, Brigitte. Well, it's nothing very special. Try and be nice to people, avoid eating fat, read a good book every now and then, get some walking in, and try and live together in peace and harmony with people of all creeds and nations. Oh, well, there we are. Here's the theme music.